We've all heard about magnets, and most of us are familiar with one of its most obvious property, that of attracting materials such as iron. Magnets can be of any shape, any size. Some shapes are like the bar magnet, cylindrical magnet, or even a horseshoe magnet. All magnets have got two poles, a north pole and a south pole. But have you ever wondered why they are called so? Well, if we freely suspend a magnet like this, the pole that points towards the north is called the north pole, and the one that points towards the south is called the south pole. If we slightly disturb this magnet, it would come back to its freely hanging approximately north-south direction. This property was used by travelers since the olden days to locate direction. A compass needle, which is a freely suspended magnet, was used by them. The tip of the needle is the north pole and the tail the south pole. The tip of the needle points approximately in the north direction. Now, what would happen if we bring a magnet close to this compass needle? The needle gets deflected. Now, if we bring the other pole of the magnet close by, then this time the needle gets deflected in the opposite direction. Do you know why this happens? When we bring the north pole of the magnet near the tip moves away, because like poles of two magnets repel each other. On the other hand, when we bring the south pole of the magnet near the tip moves closer, because unlike poles of two magnets attract each other. So, we can say that when two magnets are brought close to each other, a force of attraction or repulsion acts between them. Have you ever experienced this force? We will first bring this magnet close this way, and then the other way. What do you feel? For every magnet, there is a region around it in which this force can be experienced. This region is called the magnetic field of the magnet. But how do we represent this magnetic field? Let us see that. We have an overhead projector here. We place a transparency and a magnet over it. We will mark the north and the south poles for it. I will sprinkle some iron dust around it. What do we observe? The iron dust gets arranged in a pattern. Now look at this pattern carefully. Do you notice these lines along which the iron dust gets aligned? This pattern of lines is used to represent the magnetic field of this magnet. These lines are called field lines of a magnet. But magnetic field is a vector quantity which has both magnitude and direction. So, how do we find the direction of magnetic field? The direction of magnetic field at a point is taken to be the direction in which the north pole of a compass needle points when placed at that point. So, let us try and find the direction of magnetic field lines of this magnet using compass needles. Remember that the magnetic field lines of a magnet are not confined to a plane, but are in a region all around the magnet. We can observe that the field lines emerge from the north pole of a magnet and merge at the south pole. We know that magnets have a magnetic field associated with them. But is there any other way of generating a magnetic field? Well, till the beginning of 19th century, it was thought that there was no other way. Then something was between electricity and magnetism, and it was first established by Oersted. We can perform an experiment similar to Oersted's experiment. We have a wire and a battery eliminator. Let us connect the two terminals of the battery eliminator to the two ends of the wire. Let us place this compass needle near the wire. We will switch on the current. Notice what happens to the compass needle. What do you notice? The compass needle got deflected as soon as the current is switched on. The effect on the compass needle is same as though a magnet is brought near it. If we switch off the current, let's see what happens. The compass needle comes back to the initial north-south position. Let us try again and switch on the current. The deflection is there again. So, what can we conclude from these observations? We may say that a current carrying wire behaves like a magnet, or we can say electric current through a metallic wire produces a magnetic field. Let us now reverse the direction of current in the wire and observe what happens to the compass needle. The direction in which the compass needle pointed also got reversed. So, we have observed that the direction of magnetic field associated with an electric current depends on the direction of current. But what is the pattern of magnetic field lines due to a current carrying wire? To find this out, let us do an activity similar to the one that we did with magnets. Here we have a perspex sheet, a wire is kept perpendicular to it, a battery eliminator. Let us put some iron dust around the wire. We will switch on the current now and tap this gently. Do you notice a pattern? We already know that if we sprinkle some iron dust in a magnetic field, it arranges itself along the magnetic field lines. So, this pattern indicates the field lines of the magnetic field around a current carrying wire. Look at the pattern carefully. Do you notice a pattern of concentric circles? The field lines are concentric circles around the wire in a plane perpendicular to the current flowing in it. What is the direction of magnetic field lines due to a current in a wire? Let us find that out using some compass needles. Now, let us reverse the direction of current through the wire and see what happens to the compass needles. If we compare this pattern with the earlier one, what do we notice? When we reverse the current in the wire, the direction of the magnetic field also reverses. So, we can see that a definite relationship exists between the direction of current through the wire and the direction of magnetic field around it. But how can we remember something like this? Well, there is a very convenient way. Imagine wrapping the fingers of your right hand around the wire in such a way that the thumb points in the direction of the current. Then the fingers wrapped around the wire will point in the direction of the field lines. This rule is called the right hand thumb rule. We can do the reverse, and this would be the direction of the field lines. We have seen that a current carrying wire behaves like a magnet, and if we bring a freely suspended magnet such as a compass needle close to it, it gets deflected. Now, suppose if we were to suspend a current carrying wire in a magnetic field, what would happen? Well, let us try it out. Suppose we bend a wire in the shape of a small swing and hang it in such a way that it is free to move. And if we bring a strong horseshoe magnet and place it like this, we will now switch on the current. Observe what happens. Well, wasn't that dramatic? As soon as the current is switched on, the wire experiences a kick. Observe it again. Well, like two magnets, when brought close or in each other's field, experience a force of attraction or repulsion. This wire also experiences a force. Now, if we were to reverse the direction of current in the wire, will it experience a kick in the opposite direction? Well, let us try that. So, when we reverse the direction of current in the wire, the force on the wire also reverses. To find out the direction of force on a current carrying wire placed in a magnetic field, we use a rule, Fleming's left hand rule. According to this rule, if the current carrying conductor and the magnetic field are mutually perpendicular to each other, then the force on the conductor is perpendicular to both. If this were to show the direction of current and this finger the direction of external field, the force on the wire would be given by the thumb. Let us apply this Fleming's left hand rule to our experimental setup. From the battery eliminator, we have the current in this direction, the magnetic field like this. So, the direction of force will be along the thumb. If we now reverse the direction of current in the swing and apply the Fleming's left hand rule, the fact that the force acts on a current carrying wire kept in a magnetic field is the basis for making motors and other useful machines. Can you recall what you have learned today? A wire carrying electric current is surrounded by a magnetic field. The direction of the magnetic field around the current carrying wire is given by right hand thumb rule. If a current carrying wire is placed in an external magnetic field, it experiences a force. The direction of force on a current carrying wire kept in a magnetic field is given by Fleming's left hand rule.